Thank you, Curtis. And it is a real pleasure to be here. I was not expecting to be here, but I'm really glad that I'm here and I'm going to be your speaker today. Actually, I have a minimal, almost an infinitesimal involvement with this talk. And this talk is actually covering topics from Zach Tonks's PhD thesis with James Davenport. And yeah, we'll be talking about the practical evaluation of quantifier elimination methods. And yeah, for that, I will start with notations. I will give some background information and then move into the details of the thesis. As I said, this work is related with Zach's thesis, which is available on James's website right now. And there's also a paper published that is related with this thesis, also related with the Maple implementation Zach did in Communications in Computer and Information Science journal. And the package's name that Zach wrote is quantifier elimination, which is soon to become a native part of Maple. So it is being implemented in Maple now as we speak. And yeah, we will start with an introduction. I will give some notation and basic introduction. Then we will talk about Lazard projection and lifting a little bit. Then we will talk about equational constraints, virtual term substitutions. I will leave some notes about the benchmark that Zach did, and then we will talk about the future of this project, and that is basically going to be the talk. All right. So throughout the talk, if you see these letters, and if I'm not specifying them in a different way, these are what they're supposed to mean. So A is the number of alterations of quantifiers. So here you see the quantifier there exists, followed by 2 for alls, and followed by another there exists. So it is an alteration, 2 alteration of quantifier. So there exists a for all to there exist. So A is 2 in this case. C is the number of equational constraints, which is the polynomial set equal to 0 in our Tarski formulae. And that is the number of them. D is the maximum degree of the polynomial in any specific variable, not the total degree. M, if you ever see that, is the number of polynomials, and N is the number of variables that we use. Okay. So let's talk about the history a little bit of quantifier elimination. In 1951, Tarski showed that you can do quantifier elimination with polynomials with rational coefficients. It's decidable. And Collins later in 1975 came up with the cylindrical algebraic decomposition idea. And that has a double exponential complexity in the number of variables. Okay. And that is because every time we eliminate a variable, we square both the total degree and the number of polynomials. So everything doubles at every projection while we're getting rid of one variable at a time. Then in 1984, McCollum said, if the problem is well-oriented, if some certain polynomials do not vanish with some certain properties, then you can just you can simplify this complexity a little bit. It is still doubly exponential, but instead of 2n, now we have an n. And for double exponential, this is a really good accomplishment. And then Weiss-Fenning in 1988 introduced a virtual term substitution. So instead of talking about cylindrical algebraic decomposition, now we're talking about a different scheme, virtual term substitution. And he explained how to use it and what it does, how you can do existential quantifier elimination with that for linear, quadratic, and cubic cases. Recently, in 2016, Costa actually did the algorithmic treatment of this VTS method of Weiss-Fenning for all these degrees, less than or equal to 3. So now we have these virtual term substitutions that we can implement. And one more information here is McCollum, Porosinski, and Păunescu justified the Lazard projection and lifting. Also, without the well-orientedness that McCollum needed, has the same complexity as McCollum's well-oriented setting. Okay. And this is the history coming to today. So Lazard projection, and let's talk about that and why it is maybe different or maybe something that we would like to use instead of McCollum is as follows. So rather than McCollum's order invariance, where you need to pick an order in McCollum and do that, in Lazard projection, we need the Lex least invariance. It is on a variety. When you look at the polynomials, the Lex least monomial of f should be expanded in a certain way, where you know the roots for each and every variable. And this is desirable. And yeah, although just as in McCollum, you have trailing coefficients, not all the time, but sometimes you have trailing coefficients. Complexity-wise, they are trivial, so it doesn't change much in that regard. And the main key difference is, since you know the Lex least monomial of f, if you see that your polynomial f is 0, that it vanishes on a variety S, then you can divide this polynomial, divide f, and simplify the degrees with this part, with this big chunk of polynomial. And that is actually just to lower the degrees. And Tonks's thesis, so the quantifier elimination package that is going in Maple now is the first implementation of this, certainly in Maple. That is the first implementation that we know of, and that is certainly Maple. Okay, and what is an equational constraint, and how does it come into play? So Collins said, what if in our Tarski formula, when we have so many polynomials and just constraints on them, what if one of them is a straight up equality? So what if we have f is equal to 0 and some more polynomial constraints, where this hat phi is m-1 polynomials in GI? And McCollum answered this saying that that would reduce the complexity quite a lot. So, and then we won't really need to take the square of the number of polynomials in complexity, but it will drop to just the number of polynomials. So from a complexity point of view, instead of having the big O of m squared complexity, if you have an equational constraint, you can just have big O of m complexity. And that is because instead of having all the resultants between your function f and all the other g, you can just think of it this way. So think about the resultants in between g's when f is 0 on that variety, that is proportional to all the resultants between f and the other polynomials with respect to another variable y. So instead of just going through all of this resultants between f and g, you can just do your projection x in one less degree. And that is a big accomplishment complexity-wise when we're talking about double exponential complexity. And later he generalized that to having multiple equational constraints, not just one, but just c of them. And this reduces the double exponent of m from n into n minus c. So this is a really significant drop in complexity. Still double exponential, but significant drop. Okay, and then in 2016, Bradford, Davenport, England, McCollum, and Wilson generalized this to where only part of the formula has equational constraints, and for truth table invariant CAD. And even later, so much so till last year, England, Bradford, and Davenport said that we can even do pre-processing. We can use Gröbner bases rather than just having iterated resultants to reduce the degree growth. We can just use the Gröbner bases as we like to drop these degrees. But the point is, all of this was done for McCollum projection. And in Zach's thesis, we want to use, he wanted to use, James wanted to use, they wanted to use Lazard projection. So this chain should start from the beginning again. And in Zach's thesis, it actually does, that he can deal with one equational constraint at this time. And to advertise another talk, the following talk, we should say this. Sometimes we can think that nullification is not a problem in Lazard projection, but that is not true. And to see examples of that and how to deal with it, please wait for Akshar's talk, which is the next talk in this session. And as I was saying, in Zach's implementation of quantifier elimination, he implements a single equation constraint with no nullification, when the variety where the polynomial just vanishes is actually of dimension 0. Okay, now another quantifier elimination technique that we mentioned, the virtual term substitution. And for that, as we said, that is for existential quantifiers. So if you start with an existential quantifier and a Tarski formulae, so there is an x and all of these constraints in t for variables u, however many variables in u there is, and x. Say that it is a negation-free combination of integral polynomial equations and inequalities. What virtual term substitution tries to do is to try to find a finite set of if statements called guards and sample points so that you can change your existential constraint, get rid of this variable x, and move on to a disjunction where you can just check the guard condition and do your virtual substitution into your Tarski formulae to get the answer out of it. And as we said, this is degree limited. So it only applies for linear, quadratic, and cubic terms at this moment. The research is done for them. So if this succeeds, if we can go from the existentially quantified Tarski formulae to the right-hand side, it means that we eliminate x. The variable x just goes away. And it should be said that A, the number of alterations in quantifiers matters a lot here, because whenever you go from a there exists to for all statement, you need to do a negation of the whole Tarski formulae to get a there exists statement, and that makes all the disjunctions into conjunction. So this virtual term substitution is actually heavily dependent on this number of alterations of quantifiers. Okay, let's look at an example of a virtual term substitution and how it looks. So let's think of it this way. We have two formulas, ax minus b is equal to 0 and cx plus d is greater than 0. This should be satisfied. And if you were to say, is there an x that satisfies these? Naively, this would mean that you're just looking for solve x here and plug it into the next one, and that needs to be satisfied. So naively, this would mean c times b over a plus d needs to be larger than 0. But in our language, when we're using integers, this division by a doesn't mean anything. Plus, we do not know what a is supposed to be as a variable. So there are so many things to consider. So division doesn't exist, and we don't know what happens when a is equal to 0. These are things to consider. So you can try to eliminate this problem in multiple ways. One of them is that your guard needs to be just not equal to 0. So one of the guard is just a cannot be 0. And then you can try to clear the denominators manually, keeping in mind that a also might be negative. So a is not 0. And if a is negative, this would change signs. So you can multiply both sides with a squared instead of a to clear the denominators. So here's one way of eliminating x from the original statement going into a x-free statement, which people call W. But here, as you can see, the degree in A was appearing linearly, and now it is a quadratic. But this is not the only way that you can get rid of x. So yeah, as we said, therefore this eliminated the quantifier there exists x. But yeah, everything was linear before. Now A is a quadratic. But there's another way where how you can reduce this x, how you can eliminate this x. And that is you can just split this not equal to 0 cases into 2. You can say when A is positive, we have this inequality, and when A is negative, we have this other inequality. And here, as you can see, we paid the price in number of branches of different things to check, but everything is linear, still linear. Okay, this is just one example, maybe how we would do a virtual term substitution. And let's look at a quadratic example. Suppose that x occurs in this form. So there exists x where we have a quadratic in x and a Tarski formula that has x's in it. If you look at this, for that to be equal to 0, you definitely know that the discriminant of this quadratic must be positive. So it was a linear equation variable b. It is definitely a quadratic in b now. And there are even special cases when a is 0 and b is 0. And this creates a lot of details. And Koshta actually deals with these details in his writing, in his thesis. So devil's in the detail. So you got to be careful about these things. And as we were saying, the guard, when you look at the guard that comes out of this, it was the original statement was linear in B, and now it is in quadratic in B. So sometimes when you look at these guards, the degrees in variables can go up. So which also means that how can we control them, or how can we keep the degrees down? Because we can only do virtual substitution up to degree 3. So if we do virtual substitution in a successive manner, and if the degrees go above 3, we cannot do virtual substitution anymore. So, and what is in Zach's thesis? What is in the quantifier elimination package that is going in Maple now? Zach implemented the virtual term substitution up to user control degree being less or equal to 3. And I believe, and I couldn't find any evidence against it, that this is the first implementation in a public Maple package version. So it is the first implementation of that in Maple. Maybe it is in Synrac, but when you look at the documentation of Synrac, it actually says that they have up to degree 2. So maybe the documentation is not up to date, but I believe that it is the first implementation in a public Maple package. So the case D equals 3 is believed to be correct, but it needs quality assurance even more. So there are many pages in Koshta's thesis where he's being careful about it. Now Zach is working tirelessly about it, that he's making sure that whatever goes into Maple is quality assured and it works perfectly as it should. And one more thing, as I mentioned, in CAD, the order only affects the running time. So the order of variables that you choose to eliminate only affects the running time. But for virtual term substitution, if the degrees go up, you cannot really use the virtual term substitution again. So it is a big consideration of how the order should be chosen. All right, and now I will just go to the benchmarking part of the thesis, where Zach talks about survival plots. So not necessarily single problems and how fast they are, but just pressure tests on the code against the other codes available. So the first one that I'm going to talk about is the variable ordering generation and full projection per strategy survival plot. So he collects, Zach collected many examples, many data sets, such as Wilson's example bank, such as Synrac data place, and so on and so forth, and try to just apply his code on these. And when he looks at different methods, different strategies to do variable ordering generation and full projection of the polynomials, he sees that the heuristics, the variable ordering choices of the sum of degrees, SOTD here, and the number of distinct real roots turn out to perform really, really badly. Greedy performs quite well. And these three, the Brown heuristic, the regular chains heuristic and the equational constraint heuristic seems to work quite similarly. And the regular chains heuristic, he also notes that inside Maple, the regular chains heuristic is actually the Brown heuristic anyway. Okay. And to explain what this graph is, once again, it is a logarithmic time scale. So, and it is number of problems that has been solved without going over time, without going the threshold time. So this doesn't necessarily say that they have solved, this algorithm solved the same problem or anything like that. This just says the number of problems solved by these algorithms. The greedy is the most, greedy can solve the most problems and the rest can solve other ones. But yeah, they are not necessarily solving the same problems. Okay, the next one that I want to show is the CAD implementation timing survival plot. And here, Zach compares 3 different packages: the regular chains that is already in Maple, the projection CAD that is implemented by Matthew England, and quantifier elimination, which is Zach's own package. And it should be said that the regular chains outperforms both, but quantifier elimination also does a commendable job. And here, I should say that this is without virtual term substitution. He does not use any virtual term substitution in quantifier elimination. Again, this doesn't mean that they are solving the same problems. They're just saying in the given time threshold that quantifier elimination can solve up about 55 problems. Regular chains can solve about 75 problems, so on and so forth. And he actually mentions in his talk in the Maple 2019 conference, Zach actually mentions that there are many examples of quantifier elimination package that it can solve the problems much faster than the regular chains itself. But with the threshold and with the data set, regular chains actually outperforms. Now, the last benchmark note that I want to make is the quantifier elimination survival plot. And here there are many different strategies and many different packages. So here are the ones that I should mention: QEP CAD, Chris Brown's implementation. So Zach compares it with his implementation. So QEP CAD performs the worst in this survival plot challenge. Synrac seems to be outperforming all of them, and regular chains is still quite performing quite well. Then we have 2 clusters of Zach's package, one coming from the partial quantifier elimination, meaning that it is not using the virtual substitution. That is this gray and orange part. So, and the other group is with different type of heuristics on the virtual term substitution variable choices. There's this cluster where you only see green, but there, I assure you there are 2 more colors there. Those are the poly algorithm methods where Zach's code uses the virtual term substitution whenever it can. And it is commendable because Synrac is 18 years old, regular chains pretty much the same. And this brand new package can almost, I mean, it comes comparably close to regular chains at the very least. It should be said. It's really commendable that there's a chance that it would go over. And moreover, I should say that Zach is being cautious in this survival plot that he's not even using the degree 3 virtual substitutions. So he is going all the way up to degree 2 virtual substitutions. And I believe it would have been much closer if he were to use degree 3 virtual substitutions too. Okay, so the final verse.
You know, you're at 305.
Yep.
So
just the final verse. This is the last slide. So yeah, the 4 things that I want to say is there are some challenges going into the future. We should understand what well-orientedness does, and we should compare McCollum and Lazard projections, and also compare Lazard projection and equation constraints to see how we can get better. Explore this difference between the W prime and W, like how we do the virtual substitution matters a lot too. In particular, we should look at the problems like the one from Brown and Davenport, where this changes in quantifier matters a lot. And can this simple idea of splitting things in virtual term substitution solve these type of problems? And as Matthew England said yesterday, we should create and find new larger data sets with representative data. And with that, yeah, sorry for scaring you. I'm not going to go over time, but yeah, thank you so much.
Thank you. All right. Do we have any questions?
Yeah, I could ask a question.
Sure, yeah.
I have two questions, but if we can, there was on the graphs of the heuristics, all the different heuristics. I was gonna first of all, I was gonna say that NDRR is a heuristic really tailored to CAD. So I'm not sure it makes sense to use a VTS. So I'm not really surprised it doesn't do well. But my question was, what is EC heuristic?
It is equational constraints heuristic, he says.
So that's a heuristic for selecting your equational constraint. It's not a heuristic for selecting a variable ordering. So I was a bit confused about how it was being used to select a variable ordering. I mean, this is virtual term substitution, so I don't think there is equational constraint selections to be made.
I believe, and James should correct me if I'm wrong, so this is not virtual term substitution itself. So this is taking examples from Wilson's list, which has a bunch of polynomials. It has a Tarski formulae, and then tries to find the variable ordering in the best possible way that it can.
A variable ordering for VTS or for CAD?
For CAD. Let me
CAD,
check with details in Zach's thesis. I'll get back to you offline on this one. Good question, okay. Matthew.
In either case, I don't see the EC heuristic was for selecting which EC to use, not for selecting a variable ordering. So that kind of didn't make sense to me. And then my other question, which is a more broad question, is what is the data that's being experimented on? So I can see you've got kind of over 1,000 problems according to the graph. So where did they come from?
Okay, so there are other sources too. I have taken notes that Zach noted in his thesis. So he picks all the problems from David Wilson's example bank from 2013. He takes the whole SynRec database. Then there is the Shamir Cube, I guess. He takes, then there are two more sources at the very least that he collected problems from. And some are just, some are for quantified, some are not. So he actually gives many more graphs of survival plots where he either does only CAD and sees which algorithm is the best, or does quantifier elimination and for the quantified problems and tries to see which algorithm is the best. He takes economics examples that he could find. There's a big data set, which is also available in his thesis, that you can actually get the whole database.
So I guess my plea to Zach or you or whoever is if for those examples that are not already in the SMT-lib, please submit them to the SMT-lib, so we can try and have them all in one place. I could ask another question, but I don't want to dominate. Does anyone else want to ask one?